Okay, starting off chapter 2, we were talking about quadratic functions. We know normally we see a quadratic function in the form ax squared plus bx plus c. Like in the quadratic formula that you might remember for solving quadratics, we use those a, b, and c's to solve for the zeros. Let's think back to chapter 1 where we talked about graph transformations. And if we're thinking about the basic graph, x squared, how these 4 different graphs have been transformed. Remember that number in the front, such as 1/3 on letter A, is a vertical stretch or shrink. Since that 1/3 is smaller than 1, that is going to be a vertical shrink by a factor of 1/3. Letter B still just has a number in front, which is going to be that vertical stretch or shrink. Since 2 is bigger than 1, it is a vertical stretch by 2. Letter C, we have a negative in front and we have a +1. Since the +1's on the outside, we know that's a vertical shift, not a horizontal shift. The negative is outside the function as well, which means it's going to be a reflection over the x-axis. And then again, that 1 is a vertical shift up 1. Letter D, we have a transformation inside parentheses and outside parentheses. That inside is horizontal, left or right, and it's always opposite what we think, so that is left 2. And the 3 on the outside is vertical, down 3. And that is all review from chapter 1 when we talked about graph transformations. The form that we're going to get to um, we want to get to, because it's easy to work with, is the standard form of a quadratic, which is a times x minus h squared plus k. The reason this is a good form is because hk is the vertex point of the parabola, whether it's opening up or down. If that number on the outside, that a value, if that's positive, then it opens up. If it's negative, it opens down. And that plus k, obviously, if we're talking about transformations, that's a vertical shift, and the H is a horizontal shift. So describe the graph. To describe it, we need to get it into that standard form so I can tell you which direction it opens, what the transformations are, and what the vertex is, since it's asking us to identify that vertex. However, this is not remotely in that standard form. So we have to think back to Algebra 1 or Algebra 2 to when we had to do completing the square as one of our form, if you remember doing that to solve quadratic equations. We're also just going to use that here to rearrange this equation to get it into standard form. So we're going to complete the square. We're going to start by looking at the first 2 terms, the 2x squared and the 8x, and we're looking at a number that we can take out of both of those terms, and that number is, of course, 2. And that 7 will stay out there. So now we have this new b value. That number in front of the x is going to be referred to as our b value. Remember a, b, and c. What we're going to do to complete the square is we need to do b over 2 squared, and we're going to add and subtract that to our equation. If we add and subtract it, then we're really not changing anything. We're really just adding 0, but it is going to help us do some function manipulation to make this a little bit more friendly of an equation. So in our case, the b over 2 squared that we're going to add and subtract in our equation is 4. So within the parentheses, we're going to add and subtract 4. Why do we do this? Well, because if I look at just the plus 4 with the x squared and the 4x, that's going to factor really, really nicely, and we can rewrite it in that standard form. So I need to get that -4 out of there. I'm always going to keep the positive inside the parentheses. I'm always going to kick the negative out. So when I kick it out, I have to keep in mind that the 2 is going to be multiplied to it as well. So it's going to actually be -8 on the outside to combine with the 7. So the x squared plus 4x plus 4, the purpose of doing this is to try to get it into that standard form. So this is going to be x plus something squared or x minus something squared. And in this case, it's x plus 2. Squared would get us back to the x squared plus 4x plus 4. Okay, so I have not changed this equation at all. This is the exact same equation, but now I can tell just by looking at it that we have a vertical stretch of 2 from the outside. Since that number is positive, it opens up. It's going to be moved left 2 and down 1. I can tell all that just by being in this special form. I can also identify the vertex. Obviously, the left or right and up and down direction is going to indicate what your vertex is. So since the entire parabola was moved left 2 down 1, then our vertex is -2, -1. Remember, that's that HK. I'll go back to show you that equation here. This HK here is where we got that vertex, but we can also relate it to our transformations that I wrote up above of the left 2 down 1. That also tells you what your vertex is going to be. All right, let's do that again. Describe the graph. So again, we're going to get it into that standard form so we can describe what the transformations were, which direction it opens up, where the vertex is, and identify any x-intercepts as an additional step this time. So that standard form is actually not super helpful for finding the x-intercepts. I'm going to do that right away. I'm going to set the function equal to 0 and solve for those x-intercepts before I do all the rearranging. Because if I do all the rearranging, I'm just going to have to undo that in order to make this a friendly x-intercept solving equation. So let's set it equal to 0. And of course, there are multiple ways to solve quadratics. If you can factor it, that's always the easiest way to do it. I don't like that that first term is negative, so I'm going to take a negative out of everything. Now let's see if that factors. Really, I can just divide the negative out. Well, since I'm only solving for x-intercepts here, I'm going to obviously keep the negative when I do the rearranging, but let's see what this factors to. It's -6, and we need the factors of 8. That would get us to -6, so that would be -4 and -2, meaning our x-intercepts are 4 and 2. Let's go back to the original. And the first step we're doing is looking at the first two terms and what number can I pull out of the first two terms. That's going to be that negative. We don't want that negative inside the parentheses when I'm trying to complete the square. So that makes this -6x. And I'm going to do that b over 2 squared Doesn't matter that the 6 is negative. Since we're squaring it, this is still going to become 9 that I'm going to add and subtract inside the parentheses. +9 and -9, because remember, that's really just adding 0. I haven't changed anything. Kick out the -9 and distribute that negative to it when you kick it out. So it becomes +9 on the outside. And this factors then, that's the point of doing the completing the square, becomes x minus 3 squared. How the heck did I know that was 3 just by looking at it? Well, if you look up here at here I'll circle the -3. Before you square it, the b over 2 is exactly what it's going to be when you do the factoring step. So negative 6 over 2 is negative 3, which works out great as a little trick to help you if you have trouble with that factoring. So now that we have it in that standard form, we can figure out what the transformations were and what the vertex is. So we have a reflection over the x-axis, that's that negative, which means it opens down. Then I have a movement to the right 3 and up 1, which makes my vertex 3, 1. Okay, let's keep going. So writing the equation in standard form, I'm going to just rewrite up here. A times x minus h squared plus k is that standard form that they're referring to. Write the standard form of the equation of the parabola whose vertex is 1, 2, and it passes through the point 3, negative 6. So remember that the vertex is hk. So now that I see the standard form of the equation and I know what the vertex is, I can plug that h and that k in. X minus 1 squared plus 2. I still have too many unknowns though. I have a, I have x, I have f of x, but I do know that that point, 3, negative 6, I can plug that in for x and f of x, or y would be the same thing. So negative 6 equals a times 3 minus 1 squared plus 2. Now I only have one unknown. Now I can solve for a. Let's see, 4 minus 2 squared is 3 minus 1 squared is 4. Subtract the 2, and a is negative 2. So the standard form then, I'm just going to have to pop that negative 2 back in here. My standard form is negative 2 times x minus 1 squared plus 2. Okay, there's kind of a little shortcut to finding the x value at the minimum or the maximum. And if you have it not in standard form, but if you have it in the ax squared plus bx plus c form, these are the a, b, and c that they're referring to here, you can find the x value location of the max or the min just by doing the opposite of b over 2 times a. And that will tell you exactly where that minimum or maximum occurs, and you can tell whether it's a minimum or maximum based on the value of a. If a is positive, then it's opening up, then that's going to be a minimum. If a is negative and it opens down, then that's going to be a maximum. Okay, so I think, have seen this equation when we were talking about clearing the fence over in chapter 1. So here's our flight of the baseball. X is horizontal distance. F of x is vertical distance. What is the maximum height reached by the baseball? So since a is negative, I can tell that it's going to have a maximum, and I can do, it's the opposite of b over 2 times a. b is 1, so we'd have negative 1 over 2 times the number in front of the x squared term. And that's 156.25. Since this is an x value, this tells you the horizontal distance where the maximum occurs, but it doesn't tell you what the maximum is. To figure out what the height is, you're going to have to plug that horizontal distance into the function, and that will give you the height. So I'm going to plug it in everywhere I see an x. It's going to go to 156 into 25 hundredths. And my calculator tells me that that simplifies to 81.125 feet is the height of that. Okay. A soft drink manufacturer has daily production costs of C, this function C, where C is the total cost in dollars and X is the number of units produced. Estimate numerically. That does not mean we're solving anything. That does not mean we're graphing anything. Numerically means we're looking only at numbers, so that tells me that we're going to use some sort of table. Estimate the number of units that should be produced each day to yield a minimum cost. So this is the smallest C value or Y value in our case. Since we're going to be looking at the table, we need to look at X's and Y's. So let's get our calculator out, clear out anything that's there, and type that function into our Y equals screen. So there is a table function on your calculator. It's right above the graph. If you do second graph, you can always look at a table. But we are going to need to manipulate that because right now if I look at the table, it's going to be starting at 0, which is good, but it's only going by ones, and it would take us a really long time to scroll around to try to find where this Y value is the smallest. So I'm going to go to my second window, or second table set. Starting at 0 is fine, but I'd like to start at a bigger step, a bigger interval, and I say we start by going by hundreds. And we're going to try to locate the 200 values where the Y value is the smallest so we can narrow down the window from there. So let's go back to second graph. Let's look at that table. Now that it's going by 100s, it's a lot faster. I'm going to keep going until that Y value bottoms out and turns back around. Okay, so I see at 1100, 4550 is the smallest Y value. It turns back around and goes up after that. This is a parabola, so we know that it's going to bottom out. So I'm thinking that I'm going to go back and manipulate my table a little bit more so that I can see if this happened between 1000 and 1100 or 1100 and 1200. So I'm going to go back to the table set, start at 1000, and I'm going to go by tens this time. Okay, so I'm going to keep going again. Now it's going by tens. I might have to go a little bit further to figure out where that bottoms out. Okay, so I see at 1090 here, it's actually the lowest. So I'm going to narrow it down one more time and go by ones. I'll write our steps down here. Start with 100s. Narrow down. Start at 1000 and go by tens. That's what we did here. Narrow down. And this time we're going to start at 10, I think 1080. And go by ones finally so we can get the exact value. And scroll until we see the bottom out. Okay, I actually see 3 values with the exact same cost. So any 3 of those would be our answer. 1090, 1091, or 1092. So oops. That would be our answer. And that cost was 45, 45, 50. probably put a label here, units. There we go. One more question in our section here today about quadratics, and that is about hairdressers and cosmetologists. The number in thousands of hairdressers and cosmetologists in the United States from 1994 to 2001 is modeled by this quadratic from 4 to 11, where 4 is 1994. Determine the year in which the number of hairdressers was the least. So let's remember our trick here. The fastest way to do this, if we're doing it algebraically, is to do that negative b over 2 times a. And that will give us the t value, in this case, since t is our variable, where the max or the min occurs. Since this opens up, it would be a min. So the opposite of b over 2 times a, which happens about 5.8, which means this would be during the year 1995. At some point. All right, our homework for section 1 is down here, and that was 2.1 for pre-calculus.